Hi, Griffin. It looks like only you so far.
Oh, hello. We're having some problems with the video.
Welcome to Blue Jeans.
Hi, Dax.
Hey, I don't know where my people are, but we have Grandparents' Day today at school, so there's all sorts of confusion because people have a bunch of grandparents and.
Okay. You have school on Monday, right? Both of you?
Yeah, I do.
Okay. And what about the Monday after that? Fridays, Mondays. Like next week, it's all. The way I see here, I have the April 6th week. When is that? It's next week. I don't know why we have only one day according to the calendar, but we should meet on both days.
Okay, I can meet on both days, but our school technically has Monday off, so I mean I can definitely meet though. So
is it Monday off next school?
Next, go ahead.
Is a Monday?
Yeah, we have classes Monday, so I'll be there.
And what about you, Dax?
We don't have school, but you mean next Monday or the Monday after?
The next Monday.
Next Monday. Yeah, we don't have school, but I can still attend if you'd like me to.
Yeah, I think so. We should.
Okay.
If you have the Blue Jeans, the thing, you can attend from home.
Yeah.
Right. So, because we had a long spring break and we can keep doing this. All right. So.
Okay. All right.
And I know, I don't know what happened to Nolan. He's not attended. He wasn't here last week on Monday and not today also. Philip said he won't be here, so that leaves just two of us so far, three of us. Okay, so let's actually continue and let them catch up if they have to, because we kind of keep missing too many classes. So to go back and do what we were trying to do, if you remember, that we are trying to create networks or graphs. And the uses of networks and graphs, it's all over the place, starting from Facebook to documents, email doc. Like for example, if you create a crawler which actually goes and links the different documents, is doing network traversing. Like it starts off from one page and then reads off the link and then goes to some other page and then reads off the link and then it kind of crawls along that path. Right? So all these things are really all networking applications. And the first thing we did was, okay, if that's the case, how would we even represent a network? And we looked at three potential ways of doing it. There was one was to make it a list of edges. Just keep a list of edges. That's fine, like a long list of edges. But if you do that, the space requirement is just one line per edge, So it's not bad as far as the space requirement is concerned, but when it comes to other things, it wasn't that good. Where's my... Okay. So if you create it as a list of edges, the space only needs E. Adding an edge, of course, just add to the end. But when you're trying to look for edges between, like, you have to go through all the edges. So if you have a long list of connections, that makes it pretty bad. The other part, the easier one, which actually is more intuitive, is creating an adjacency matrix. We create a V by V matrix. The problem with that is the V squared. And we end up having what's called a sparse matrix, where if you think about a network, a street network, you may end up with 1 million nodes or hundreds of thousands of nodes, but most of them are not connected to each other. They're only connected to the adjacent 4 or 5 nodes. As a result, you end up with what's called a sparse matrix. So this is the same problem when you're doing like matrix calculations and you're creating matrices. This is also the same, right? So you have what's called the sparse matrix. So, but the adding all these things were pretty easy. Adding was easy. To check whether there's an edge between two nodes was easy. And of course, if you want to find out all the edges that all the vertices one vertex is connected to, we have to scan through the entire row to find out which vertices this vertex is connected to. This turns out to be pretty good because this one, when we have an adjacency list, it's almost like this hashing thing. We create a list of vertices, an array of vertices, and connected to each array is a list. A list that says which vertex that's connected to.
Are you sharing your screen? Because...
Yes, I am not.
Oh, okay.
Oh.
I'm not seeing.
Oh, okay.
No, I should be.
I don't see it, so...
No, I wasn't. I forgot. Let's go. Share the screen.
Okay, there we go.
Yeah, I got it.
Bad habits. Right. So with the adjacent sparse matrix, so with the adjacent matrix, adjacency list, the space requirement is E plus V, meaning for every vertex we need an array space. Then another space for the edges it's connected to it. Right, so that's E plus V. Adding an edge takes a constant time. We can just add to the beginning of the list. Go to the array location and just insert it right at the front. Right, we can adding takes only a constant time. And then if you want to check whether there is a vertex between two V and W, there's an edge between two vertices. If there's an edge between two vertices, you have to go to the array index and then scan through the, exactly like hashing. Like you'll have to scan through the list of vertices to see is that connected to each. So that's based on the degree. And what's the degree of a vertex? A degree of a vertex is the number of links that's coming out of it. And that's a degree of a vertex. So that's vertex, and iteration over the vertices also is a degree. Right? So most likely, I mean, a good representation is that one. Given the performance of what we are trying to do, adjacency list is what we would like to use. So it's an array list of array lists. Right? An array for the vertex, and then for each of the edges there's another array list. So this is representational point. Of course, what do you want to do with a network? What's the first thing you would like to do with a network? Or what type of queries do you think you would like to do?
Search it, or like traverse it, I guess.
Exactly. I mean, that's what you would like to do. Traverse, for example, let's say you have a network and you want to, it could be a maze like this, and you want to get out of the maze. Or you want to do, like, say, suppose you want to you want to get out of this maze. Let's say you start off here and you want to find a path to get to the other point. Right? So how would you go about doing something like this? You have a maze like this. How do you think I should start traversing? I could mark these nodes, 1, 2, 3, like that. I could mark those nodes, but I want to be. I know I'm starting from A, and based on the information I have all the list of edges. So I know that which nodes are connected to which ones. That's all I have. So I don't have a spatial view of things. And that's what differentiates human beings from computers. We can look at it and say that's how you go. You don't even need a program, whereas a computer needs to scan through the list and come up with the requirement, the path. So I'm not looking for the shortest path. I'm looking for a path. So how do you think we should go about doing this?
Well, I'd say start with the first node and then just start visiting its neighbors. And every time you visit a node, mark it to make sure you don't come back. And then eventually when you're done, you're done.
So you need to mark it so that you end up not having not going back in cycles. Right? So you need to mark something. So let's say, for example, this is a type of an arbitrary. Let's say this is what we have. Right? And we want to go from node A, or let's call it 1, and node A, okay, let's call this A. Let's mark them. I, J, K, L. So I want to go from A to J. I want to find a path from A to J. Right? So let's start from A. Okay, now tell me what I should do here. All I know is I know where A starts from, and I have all the vertices that's connected to A. So what should I do?
Just visit one of the connected nodes or vertices, I guess.
Okay, so let's say I go to B. Then what next? What's next?
You could either visit C or F, but you'd have to mark that you visited B and A already, so you don't come back to it.
Okay, I can. So that's the basic idea, right? So before we start, so to be able to process these vertices, let's create a stack. We know that once we go, like, we now create a stack, and then we'll push all the vertices that's connected to A. So you start off from there and says, let's push all of them. So let's say it's G, F, E, B, D, C. right? So this we can get from you can go to the array location and push all the vertices that's connected to it. So now let's pop something out. Let's take the first one out. And so let's mark A as being visited. So we know that A has been visited. So I'm going to put an X right next to it, say that A has been visited. Right? Now let's pop something out. And let's say, for example, when we pop, we get C. Right? So let's take C out. Let's mark the C as visited, and then connect all the. Now we can do it two ways. One would be that so let's actually mark them. Let's mark them, not mark them right now. Let's put these things into the stack. So that is the neighbors that's connected to the vertices that's connected to C. Let's put it into the stack. So we're going to put B and D into this. B and D into this. Alternatively, we can mark them and put them as we are instructing, as we are putting things in. For example, when I'm putting this now you find that there are two entries of B and D in it, in the stack. We really don't need to, I mean, we could have marked it as we were adding it for the first time. That way you won't end up with two entries. Right? So if you want, we can do that too. That doesn't matter. In this case, we have to, since we are marking it, I think it's easier we mark them, because I don't end up with a big stack, but the process can be, then I don't have space to write all these things. So what I'm going to do here, that so as I'm going to push these things, the implementations can be slightly different. As I'm pushing them, I'm going to mark them saying, hey, these things are already in my stack. These have been marked. Let's pop C out and look at the neighbors, B and D. Have they already been marked? Right? So because, right. So because they have been marked, let's not put them back in. So let's take C out. C, that means C has been completely processed. All the neighbors of C has been processed. Let's pop the next thing out. Let's pop D out. See, look at the neighbors. Have they been already marked? Yes. Right? So let's pop it out and throw that away. Right? So you're removing the edges. So this is like saying, okay, I have visited I have seen all these edges. I'm going to save them to process them later, because I want to go from there to the next level. But I'm going to process C, and let's see, C's neighbors have already been processed. Now I process D. D's neighbors have already been marked. Then I process B. What about B's neighbors? They have also been marked. Let's now take E. Take E out and put the neighbor of E into this. The neighbors of E are D and H. Push them into the stack. Of course, D has been marked, so let's push H up here. Right? So H has been marked. Now let's take H out. I, J, K, L is missing here. L, M. L is there. Right? So let's take H out. Take H out, push the name. So H has been marked. So take H out, push the neighbors of H into the stack. That would be L, A, and M. So push them into the stack. So that's, the stack is going to contain L, K, M. And then pop the first one out. And look at the neighbors. The neighbors of L are J and I. Right? So, and then pop the I out, you can at this point you can pop the I out, and then I has a neighbor J. J is already there. So when you pop, you find that J is connected to it. So, right. So this way, I'm doing exactly what you said. I'm maintaining a more organized way of visiting what the nodes are. Right? Because I want to start from my source node and then expand all the way out. Right? So I can push it into the stack, and as push into the stack, so visit the node, push all the nodes that's connected to that node into a stack. Pop the first one out, and then visit all the neighbors. Now make sure that you mark them so that you don't go back in cycles. So a vertex that's been already visited once will be marked so that you don't go back and revisit the same vertex again. Right? That's what the depth first search is. Right? So to maintain which vertices I need. So essentially what it's going to do is we're going to start from here. You're going to, these are the 4 nodes. It's going to go, let's say the A is connected to those 4 nodes. We push all 4 of them. You take one more guy out of this, push the next one out, and look at the vertices that's connected to that. And then you pop the next one out. We could pop this one out. And then you look at the vertices that's connected to that. Pop this out, connect the vertices connected to that. You pop that out. So what ends up, what do you think is going to be in the stack? If you look at the search path expands like that. Go ahead, Dax. You wanted to say something?
I was just asking what the question was.
So
go ahead.
So if you look at the way the search path is growing, the search path is growing in a kind of as if you're climbing up a tree until you go to the end. It's possible that you go to that end and then there's no more nodes to visit. So you traverse back, you go back and you start visiting, expanding out like this. And then you come back, you expand like that. Right? So the ones that's closest, you're taking a path all the way along one branch, visiting to the end of the universe. You can reach from that branch, and then traverse back, step back one level back, and then visit all the neighbors, and then step back one level back and visit all the neighbors, step back, like that. And then eventually when you have visited, so you may have, let's say for example, the path you're searching might be on this side, but we won't get to it until we have exhaustively searched all these on that side. We could end up spending a lot of time searching in a place where it doesn't even exist. Like for example, you want to go from San Francisco to LA, and if you take the northern route, you'll go all the way to Canada, Vancouver, Toronto, Washington, Florida, and then because there is a path that will take you all the way like that, because you're going that way. Now, so it may not be the most efficient things for certain types of items, certain type of searches, but certainly eventually we'll find it. If there's a path, we will find it. Right? This is what's called depth first search. Right? So the search that goes like this is kind of like climbing a tree all the way to the leaf, come down a branch, go back the other branch all the way to the leaf, and then so it's searching along the branches. So the code for that would be not that difficult, right? So essentially, if you look at the pseudo code, depth first search, to visit a vertex visit the vertex, mark the V as has been visited, and then recursively visit all the unmarked vertices. And keep visiting all this. Right? So the code for that is, if you look at the code, that's what it looks like. It's a recursive call. Now in this thing that we're marking, so you're going to call a depth first search, and the method, the public method contains the graph and the source from we are going to do a depth first search. And it has a private method. It starts off at the source and then recursively calls the depth first search again, DFS method. And so it starts off marking the source as visited, and then it goes through all the vertices that's connected to that source one by one, visit all the vertices like that. Now if you look at this code, can you see the stack built into this? Can you see a stack that's built into this?
What do you mean exactly?
Like, am I using a stack?
It doesn't seem so.
Right. So if you look at the code here, so first of all, this line of course is okay, fine. I'm going to mark the vertex as visited, and then this is the list of vertices that's connected to that particular source vertex. Take one by one, and then do a depth first search based on that. Right? So you take the first vertex, do a depth first search on that. Now, if you're going to take a first vertex and do a depth first search, so let's say, for example, you have the first, when you call the depth first search for the first time, you may have a list of vertices that needs to be visited. Let's say it's 1, 2, 3, 4, 5. Take the first one out and do a depth first search on that. And then that could give you a list of nodes that's 6, 7, 8. You take the first one out. You do a depth first search on that. 8, 9, 10, 11. Take a first one out. Now, so even though you don't see the stack there, it's essentially keep doing that. Because if you look at this, these vertices that at the bottom are the ones that would be the one that's the bottom of the stack. Right? It's a stack, right? Although there is an explicit stack, creating an array of, like, it's kind of like a loop, nested loops. Right? But the nested loops, because of methods. So when you call methods, like you're calling the first method, and then the method has a list of an array of vertices. It calls a second method that has an array of vertices. It calls a third method that has an array of vertices. So it's kind of doing the same thing, but it's not explicitly using a stack. Right? So can you recognize it's the same type of thing? Like, for example, if you say, now this line here, right, that would give you the first list of vertices that's connected to it. Right? So you take the first one out. Right? You take the first one out, and then what do? we create a depth first search on the first one. So that's going to have its own list of vertices that's connected to it. You take the first one out and you do a depth first search on that. Right? So when you get to the final level, then you push everything out. Let's say we have visited all the nodes, we push this out and then take the second one out. Right? Isn't the same thing? Isn't it? It isn't almost the same thing, except the implementation is slightly different.
Yeah, I would say so.
Yeah.
Right? Yeah. So this is the exact. So I wanted to show depth first search using a stack because it's easy to compare this with the next type of a search, which is called a breadth first search. Right? So where we use what's called, we instead of using a stack, we'll use a queue. Right? So you can compare the depth first search based on a stack and a breadth first search based on a queue. Right? So this is doing exactly the same thing, except that it has methods and it has loops in it. Right? It's almost doing the same thing.
So how long does that take? Is it the number of vertices plus the number of edges? Because you're only visiting each one once, I guess?
To visit all the nodes that's connected to it, it'll take the number of vertices, number of edges, number of right? So it'll be depending on how you process it, it'll be the number of because you have to visit each, you have to consider each edge only once.
Okay.
Right? Because you'll have to take the edge out and see, okay, who is on the other side. So each edge has to be considered at least once to throw it away before we throw that away. Right? Because we'll have to pull out the edge to see who is on the other side of the. Right. So so essentially what it says is, so the proposition is that a depth first search will mark all the vertices connected to the source S in a time proportional to the sum of the degrees. So what is the sum of the degrees?
You add up the degrees of all the nodes or vertices connected to S.
And which if you connect it to E, number of edges, how is it connected to?
What do you mean exactly?
Like for example, so isn't the degrees connected to the number of edges?
Yeah.
Right. Now if you sum up, if there are n edges, what is the sum of the degrees would be? What do you think the sum of the degrees would be?
The sum of the.
If the number of
some of the degrees of like
of the
nodes
of
the entire graph.
Of the entire graph. If there are n edges.
So the n times the number of vertices, maybe? No, not necessarily.
Won't it be? Go ahead.
Well, it'll just be the number of vertices of every node added together.
So let's take this and see how many edges do we have? 1, 2, 3, 4, 5. One, 2. How many do we have here? 3, 5, 7, 9, something like that. Right? The number of edges in this graph is 1, 2, 3, 4, 5, 6, 7, 8, 9. If you sum up the degrees of the vertices, what would you get? the entire graph, the sum of the degrees.
Is it 9?
Is it 9 or is it 2 times 9?
Oh no, yeah. Because
Wouldn't it depend on the configuration of the graph?
Will it? That's my question. That's what I wanted to see. Will it depend on the configuration of the graph?
I think it probably would, because
But what happens? But see, each edge gets counted twice, isn't it?
I guess so, yeah.
Right. So if you
right.
right.
because each edge is a part of two or multiple different degrees.
The degree, yeah, part of the degrees on the inside
okay.
on the two sides, right?
Yeah.
So then the degree would be 2 times the number of edges. Right? So that's what it says by it's proportional to the sum of their degrees. So it's not exact. I mean, you could be exact specific and say it's 2 times E, but because the degree is proportional to the number of edges. And because each edge gets counted twice on both vertices. So that's why. So a depth first search will mark all the vertices connected to it in a time proportional to the sum of the degrees, and that's we can kind of intuitively see that that's how it works. And the running time, each vertex visited is visited only once. Now we could, right? In addition to this, if you want to maintain a path, hi Justin.
Sorry I'm late. I had to give like a presentation for our school holiday thing. Yeah.
You just came off your holiday thing.
Oh no, we do this thing every year where grandparents of students come and like visit school. So I had to,
yeah. That's what Dax was telling us. That
yeah.
So we were just finishing what's called a depth first search. And we could, if we have to maintain, is it possible to maintain a path? Like, is it possible to maintain the path also, not just how to get from A to B? Like, how would I maintain a depth first search? How will I do a path using this? Now, we know that we can visit all the vertices using a depth first search. The question is, can I also, in the process, maintain how to get there?
I mean, we could try to like store. Well, I mean, they're using a stack there, but we try to like store the path, and then if we don't reach the node in that particular way, then we just throw out the path as we recursively go back.
Yeah, so we can maintain an array like this. We can maintain an array and say how we got to that. Like we can maintain an array and say these are the vertices. So if you're going from one vertex, you can maintain an array to say, okay, I got to this from here, and then I got to that from here. So you could theoretically, it's easy to maintain an array called an edge to array and maintain that. Like for example, let's say, let's create an array that's like that, right? This is what's called the edge to array. Initially, I put all the vertices in it. So I have all the vertices 1, 2, 3, 4 marked all the way to n. Right? Now I visit all the vertices that's connected to 1. Let's say 1 is connected to 2, 3, and 4. Right? So I could put 1 here. Can you see that? Is it? I'm kind of drawing it on the side, but are you able to see it? Right. So maybe I should to find out the path. So what I'll do is I'll put 1, 1, 1. So right, and then let's take out 2 out. Let's say 2 is going to take us to 6. That's 5 here. 5, 6, 7. Let's say 2 will take us to 6. So we put 2 here. Okay. So this is an array of the edge 2, meaning how did I get to that vertex? You only maintain a link to the last one I came from. Right? So whenever we pop something out, we can say, okay, I'm going to pop 2 out, and 2 is going to visit 6. So I'm going to put 6. 6 says I came to 6 through 2. And then if 6 says I can go to 8, then I came to 8 through 6. Right. So now how do I if I have an array that's like this array, is it possible to find the path from 1 to 8? Right? Is it possible to do that?
Well, yeah, it is possible. Don't know exactly how, but
Well, no. So let's go to 8. Right? So let's actually, I'm going to take a different sheet here. This is insert. Right? So I'm going to create what's called an array edge 2. Let's say I'm going to create an array like this. Now I have a list of all the vertices in this array. I'm going to start from the source matrix 1. Let's say, for example, 1 connects me to 4, 5, and 8. So I put a 1 here. So 4, 5, and 8 are connected through 1. So in my stack, I'm visiting nodes 4, 5, and 8. Let's pop 4 out and see which vertices 4 is connected to. Let's say 4 is connected to 7 and 11. So this is 1 was connected. Node 1 was connected to 4, 5, and 8. I pop 4 out and find out which ones 4 is connected to. So I find that 4 is connected to 8, 9, and 2. So I put 4 here. So I can get to 4. That's, sorry, what am I doing here? That's my 4, 8, 9, and 2. So 8, 9, and 2. Let's visit 9 and say 9 is connected to 3 and 6. 9 is connected to, so 9 is connected. This is 9 and that's 9. Right? And then take 3 and find 3 is connected to 11 and 12. 11, 12, 7. So 3 is connected to, that's 3, that's 3, and that's 3. And then let's take 12. 12 is connected to 10 and 13. This is the search I end up with. 12 is connected to 10, 13. Now, this is the array I have. Based on this, can you tell me the path from 1 to 13? This from this edge to array. Based on this array.
Well, I guess you could start. Yeah, you would start at 13. See that that connects to 12.
Well, that's 12, yes. So you find out 12, that takes me to 12, right? Okay, then, and then find the parent to 12. That's 3. So I go to 3, right? And find the parent, the edge to 3, that takes me to 9. And find the edge to 9, 9 takes me to 4. And 4 takes me back, 4 takes me to 1. Right? So by maintaining an array, as you visit the vertices, as you start processing the vertices, if you can pop the numbers into, or put it into an array, then if necessary, we can go back and trace the path back. Right? So if you want to remember how to get from one node to the other node, then we'll have to maintain an internal array that marks how we got there. Right? That's how you would maintain the path.
Wouldn't that eventually just drastically increase memory usage, though?
It could, right? If you have a large network, it could actually increase that. Yes. Right? So then what we have to do is, in cases of like when we have very, very large networks, what we do is we don't want to load the entire data into the memory at all. Right? We don't want to load that. So like large databases, large queries, large number of documents, we just load what's needed and create a dynamic structure. So we don't even want the entire network to be in memory at the same time. Right? So we want to just load only the part of the data that's needed. And that's, yes, you're right, because what we sometimes when the data sets gets larger, we cannot do the entire query, the entire operation by keeping the entire data set in memory. And that's what databases do. When trying to use databases end up pulling out only the sections that's needed, not the entire thing that's needed. So that's what depth first search is. We look at a similar search, what's called the breadth first search. The breadth first search, kind of like the depth first search, but it doesn't go along. So instead of, what would happen, let me go back to my previous slide so I don't have to draw this again. What would happen if instead of maintaining a stack like this, what if I maintain a queue? So let's say, for example, I'm going to start the same process. I'm going to start with A and put all the vertices that's connected to A into a queue. So we have we put them all into the queue. That's B, C, D, E, B, C, D, E, F, G. E, F, G. Now take the one from the front of the queue. Let's take it out and visit that. Let's mark that as visited. And let's put all the ones that's connected to B into the queue. Right? So what's connected to B? A, C, F. That's it. Right? Now take the next one out of the queue. Have I visited C yet? No. So I take it out and then put all the neighbors that's connected to C, which is D and which is B, D, A. Right? I push them into the queue. Then take D out. Right? So let's see what is D connected to. D is connected to A, D, E. Take the next one out. Take E out. Have I visited E? Not yet. So I have visited C. I have visited E. Have I visited E yet? No. Come on, stop. Okay. This is this IRS calls. You know the IRS calls?
Yeah.
So he wants my tax. Okay. So let's take, have I visited E? No. Let's put the neighbors of E into this, which is A and H. Let's put A and H. So we have a queue that's building up like that. Let's take F. Have I visited F? No. So E has been visited. Mark F has been visited. Put all the neighbors in. That's B, G, B, G. Who else? A and I. Right? Now take F out. F is out. Take G out. Put the neighbors of G into that. Has G been visited? No. So let's put the neighbors of G into this, which is A, F, M, H. Take A out. Has A been visited? Have I visited A before? Guys, are you following me here or what?
Yeah.
Well, did you mark A when you first discovered all
Yeah, I
of
did.
it?
Sorry, yes,
Okay,
I did.
Then
Yeah.
yeah.
So A is right? A is visited. So I don't revisit this again. I throw it out. What about C?
Yep, visited.
Yep.
Throw it out. F, throw it out. Right? B, throw it out. D, throw it out. A, throw it out. A, throw it out. C, E, A, H. No, H has not been visited. right? So I stop at H and then push all the ones that's connected to H, which is G has been visited too, right? So what's connected? Go ahead. G, M, E, E and L.
Where's E?
E is right here.
Oh, I thought that was a G. My bad.
Okay.
I thought there were two G's. Okay.
Yeah. Right? Well.
Connected to, is that K as well? Yeah. On the diagonal.
This one here?
Yeah.
Yes. Right? So I visit H. So I mark H as been visited and then take that out, put the neighbors in. B has been visited. G has been visited. A has been visited. Take I. I has not been. So I push F, A, and M. M into this. And then I has been marked as visited. A, F, go to M. So you can see how a breadth first search works. So instead of using a stack of all the unvisited nodes, use a queue. Right? So the process is the same, except that either we use a stack or a queue. If you use a stack, it becomes what's called a depth first search. If you use a queue, then it ends up being a breadth first search. Right? And I'll say one more thing and we'll stop here. So if you visualize both, visualizing a depth first search is like visiting the tree. As I wrote before, it's like you start from the tree, the source node, and then you visit the furthest point you can visit and then backtrack. Right? So you're kind of going all the way like this and then trying to backtrack like that. And then you might backtrack and then start as soon as you visit the end of the thing, you start backtracking and you go out like that. Whereas in a breadth first search, you start off like this. And you start off like that. So you start from the closest neighbors and you grow outwards. It's kind of like a wave that expands. Right? So it discovers the ones that one hop away first. Then it starts going on that one hop away nodes, and then it starts discovering the nodes that's two hop away. Right? So the visualization of a breadth first search is like expanding wave. It expands one step every time away from the source. Unlike a depth first search, the depth first goes on one path all the way to the infinity, comes back, and then starts backtracking all the way back. That's what the depth first search looks. First search and breadth first search. We use a stack. We use a queue. Process is the same, except what we use here will result in two different types of searches. Right? How we go about processing the nodes, in which order we start processing the nodes, would result in two different types of pictures, visual pictures. Now, sometimes we want to use the breadth first search, and sometimes we want to use the depth first search. Let's say, for example, you're trying to find the shortest path. What would you use?
Breadth, right?
breadth first search, right? Yeah, so you're right, because you want to expand one node at a time and go outwards one hop at a time. Like it's that wave that keeps increasing until it reaches the point you want to be. So breadth first search, a variant of breadth first search is something we would like to use. Okay, guys, I'm going to let you go, otherwise you'll get kicked out.
Great, thank you.
All right,
Thanks so
thank you.
much. See you later.
See you Monday.